the Star Trek canon, warp drive was invented by Zephyr Cochrane in the year 20. For reaction, there's an opposite and equal reaction. In the mid-1660s, came up with basic laws of motion. They were only a hero of Alexandria 2,000 years ago with his aeropile. It's just a very simple steam engine, fire under a brass ball with a couple of vents on it, and the ball would rotate at high speed. But he didn't understand what he had, didn't describe it properly, so he didn't get bragging rights that he does. All rockets are Newtonian rockets. Action, reaction, and force equals mass times acceleration. And that's real funny that A is not supposed to be there. This is what happens when you have Microsoft products displaying an awful sleep. Yes. Okay. How you do it is the rocket science part. Excuse me. Most rockets, chemical rockets, either liquid or solid. We do it by combustion for the most rockets. Shuttle main engine, burn liquid hydrogen, liquid oxygen. That's one of the more popular combinations. Anybody know what the exhaust product is from that? Steam. Flying tea kettle. It's literally steam. Hydrogen, H2O. That's what's coming out the back end of it. The RL-10 rocket engine we have up on display up on the third floor is the first practical liquid hydrogen rocket engine. It's still in use today. Or the other popular combination is liquid oxygen and kerosene, RP1. The big F1 rocket engine we have on display out in the rocket park used RP1, refined form of kerosene. Or storable propellants, rather than an acid combination of nitrogen-based compounds that ignite on contact. Or solid rockets, the shuttle boosters there, like most solids, burn oxygen and aluminum powder. So the thing is just a giant thermite candle, all mixed together in a rubbery binder, and that's why the exhaust was a brilliant, blinding yellow white. It actually would hurt your eyes to look directly into the exhaust. Nuclear rockets, again, flying tea kettle. NERVA, nuclear engine for rocket vehicle application, which we were working towards in the 1960s and 70s, and the project got canceled. Basically, you would just take liquid hydrogen, flush it through the core of a graphite uranium reactor. Liquid hydrogen goes in, super hot hydrogen gas comes out the other end, and the efficiency, the equivalent of miles per gallon for rockets on this was about twice what you would get with a space shuttle main engine. And NASA is looking at this again at nuclear graphite core or nuclear thermal rockets. In the movie 2001, it was a gas core nuclear rocket. That's X-ray Delta 1 Discovery at the bottom. NASA is also looking at this as a way to get us to Mars and back very quickly. That would solve most of the problems we have with the crews being exposed to weightlessness and radiation for a long time. Ion engines, this is where we have an artifact that kind of connects directly to Star Trek. Ion engines, you electrify a gas and you use an electrified grid to propel the positively charged ions out the back end of the rocket, and then an electron gun fires the electrons so that you don't build up a static charge that ultimately winds up collecting all of your exhaust product around the rocket. And they are extremely efficient, where the miles per gallon measurement, say for shuttle main engine, was around 460 seconds, which is pretty darn good for a chemical rocket. These can have efficiencies ranging from 1,000 to 5,000, maybe even 10,000 seconds. Problem is, the kick is really, really weak. A sheet of paper falling on your hand would exert more force. But if you got some patience, they're really good for moving things around the solar system. Spacecraft use them for station keeping, geostationary keeping, and other communication satellites. The Dawn spacecraft, explored asteroid Vesta, and now is orbiting the Ceres, is used an ion engine to very gradually reshape its orbit so that it can rendezvous with those bodies. Again, Star Trek connection in the bottom left, in I think it was sometime during season 2, the crew, production crew of Star Trek visited NASA's Glenn Research Center, I believe, and to learn a little bit more about real space technology. And Roddenberry supposedly said, "Is there anything we can do for you?" And the answer that came back was, "Yeah, you could, maybe put in a plug for ion propulsion," because they had an ion engine they wanted to fly in orbit. Get some real-world testing on it. So in season 2, the episode Spock's Brain, which is universally reviled as the worst of the original series. Yes, where Spock gets turned into a space zombie because aliens have taken his brain because they can't figure out how to do their own artificial intelligence systems. They've got to steal Spock's brain, driven by an ion engine. So this is a ground test model of an ion engine that was flown in a sounding rocket flight. And it was a forerunner of the one that NASA was asking Roddenberry and his crew to help promote. And eventually it did fly in the early 1970s and operated for several years. It was very successful. Helped lead to what we're using now. Problem is, as I said, the kick is not all that great. You're not going to get to another star system in multiple lifetimes, let alone a TV episode. Casimir, variable specific impulse magnetoplasma rocket. Let's see why they use a name like Casimir instead. It's a lot easier. This one, instead of being a flying tea kettle, is a flying microwave oven. It's being developed by Franklin Chang Diaz, former NASA astronaut from Costa Rica, and he's working in Houston and in Costa Rica. Vacuum chamber demonstrations. Basically what you do is you use radio waves to pump energy into a plasma and electrified gas. That heats it and propels it out the back end. And it would not only be very efficient, but also be very powerful. So theoretically, this could get us out to Mars in 6 weeks instead of 6 to 9 months. That's a significant savings and greatly improved for crew health. And it's hoping to get a demonstration test unit flown in about the next 5 to 10 years. It's hoping to have one on space station to help reboost it, but that didn't quite work out. Partly because it takes a lot of electricity to make that thing work. Project Orion, this is one of the more unusual ones ever proposed. A series of miniature H-bombs set off at the backside of a rocket. Bang, 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 about 5 to 10 per second. So you can launch a supermassive rocket into orbit and then send it on to Mars and the planets in a matter of days or weeks. And they actually, the idea came out of Los Alamos in the 1950s, and they, in the late 50s, early 60s, they tested this model, which is on display at the National Air and Space Museum. They tested a unit, I think it may have been out here at White Sands, or Newton, I think it was in Southern California, using C4 and dynamite to prove out the principle. Effectively was stopped by the Nuclear Test Ban Treaty, which was the part of that banned the testing of nuclear weapons in space or the permanent positioning of nuclear weapons in space. And effectively killed off Project Orion. But folks haven't given up on it completely. British Interplanetary Society, in their Project Daedalus study in the 1970s, came up with this concept for a two-stage rocket to take unmanned probes to a nearby star system. And they were going to do it with a series of H-bombs. Deuterium plus helium-3 fused probably by laser systems, yields helium and protons and gamma radiation. And they would be able to get this thing up to about 12% the speed of light. Going out there, that would be the first stage. Second stage would then slow you down for arrival at the star system, and then unmanned spacecraft using conventional propulsion would tool around and explore the planets. Antimatter. There's that funny equation gone wrong again for some reason. E equals mc squared. Antimatter, the cure-all for everything in propulsion and sci-fi. All you need is antimatter and you're good to go, right? Where do you mine it? Yeah, it's kind of hard to come by. We see it in nature, but usually that's the result of extremely high energy cosmic ray collisions, producing antimatter particles as a byproduct. Those very quickly run into matter. Matter and antimatter meet, they annihilate, and you get pure energy. So in the simplest reactions, an electron plus a positron, which is an antiproton, will produce gamma rays at about 511 electron volts, which is a little bit more energetic than what you get at the imaging clinic. The problem is, first off, producing antimatter, which would take some banks and banks and banks of really powerful particle accelerators. Then you got to store it. So it's kind of like the philosopher's universal solvent that's going to burn through any container. It would have to be held in what is known as a Penning trap, which is a combination of magnetic and electric fields to keep it contained inside. Okay, so now you've got the genie in a bottle. What do you do with it? How do you make it work? Ultimately, it's just another flying tea kettle. You're using the gamma rays to heat the fluid, probably just hydrogen gas, and it squirts out back into the rocket, action, reaction. So it's Albert Einstein helping Isaac Newton make a rocket work. Antimatter, of course, is what powers Starship Enterprise, and in the latest movie, Star Trek Beyond, they actually went to a real reactor facility and used that as a prop. It's the warp core of Starship Enterprise. In this case, it's the National Ignition Facility in Livermore, California, where they are working on using high-powered lasers to energize and squeeze microscopic pellets of deuterium and tritium and spark the fusion reaction. So it's part of the question for nuclear fusion power, clean nuclear fusion. So they used the heart of the NIF as the warp core of Starship Enterprise, and this led to one of the better pranks ever done in Hollywood. Simon Pegg, who played Mr. Scott, was also one of the script writers, pranked the entire crew. They talked them into wearing these little dots of cream, neutron cream, to absorb, to protect them from neutron radiation coming from the reactor. Yes. Oh yeah, they got everybody. They got Chris Pine, they got Benedict Cumberbatch, they got them all. So you can see, Peg there tells us what's going on. There's Zoe Saldana, Lieutenant Uhura, getting made up by the makeup crew, who of course was in on it. Okay, jumping over to Star Wars, lasers. And actually the real Star Wars Strategic Defense Initiative developed a lot of high-energy laser technology. Lee Mirabeau from Rensselaer Polytech worked on a concept developed by Arthur Kantrowitz in the 1960s that you could use lasers to provide the heat for a working fluid. So instead of hauling a reactor along, instead of burning stuff, you simply beam the energy in with a laser into the spacecraft, which looks a heck of a lot like the jellyfish creature in the first episode of Star Trek Next Generation, like the critter from Farpoint. So you have reflectors, heat up the working fluid, and that will propel the spacecraft into orbit. And it was tested out here at White Sands, set a world record hovering flight, reaching an altitude of, I think it was about 250 feet for 10 seconds. Of course, one of the drawbacks of something like that is you've really got to make sure there aren't any airplanes or spacecraft on the other side of that beam. Could give somebody a bad day. But again, it's still a Newtonian rocket. Okay, alternatives to rockets. There's a handful of alternatives. One that we've already been using, and a few others that are in work right now. First off, gravity. We've been using gravity to reshape the trajectories of deep space probes ever since the Mariner 2 mission in the early 1960s. You fly past a planet just right, and when you come out the other side of that encounter, not only is your direction changed, you've picked up speed. So this is how we were able to get the Galileo spacecraft from Earth orbit to Jupiter in the 1990s. We had to fly past Venus and Earth, gravitational assist there, and then eventually got into Jupiter. The Voyager 1 and 2 spacecraft, when they flew past Jupiter, had their trajectories reshaped so that they then flew past Saturn, and then Voyager 2 was able to reshape and pick up velocity so that it could go outward to Uranus and Neptune. Here's the fun part. Energy has to be conserved. Energy and matter have to be conserved. You can convert one to the other, but you cannot create or destroy them. That means that when the spacecraft go past the planets and they pick up speed, they're slowing the planets down. So when the little tiny New Horizons probe zipped past Jupiter to reshape its trajectory outward to Pluto, it came out as the fastest man-made object ever. Jupiter was now going a little bit slower. But Jupiter's so massive compared to New Horizons, it's going to take a few gazillion encounters like that before you notice any kind of difference. So if you've got patience, though, this is a great way to extend your gas mileage. So if you've got first case of propulsion, space propulsion without rockets. Space tethers is something that NASA and DoD and others have been experimenting with. First demonstration with space tethers was done with the Gemini 11 and 12 missions. That was really just to experimenting with the means of stabilizing spacecraft. But with a tether, with an you reel out a copper wire, and what you've done now is built an immense electric motor. You move the conductor through a magnetic field, and you produce electricity. Or if you put an electric current through that wire, you're generating a magnetic field in the wire, and that could drag against the magnetic field on the spacecraft. Or run the current the other direction. Now you're working with it, so you can use this either to bring expended satellites and rocket stages back down into the atmosphere, or to reduce them, raise their orbit. So this is an old slide, because they're talking about using it possibly on space station as early as 2005. Well, that was 11 years ago. Jovian spacecraft 2015, nobody out there. Theoretically, it can be done. It's sort of a drip feed, but it's not getting a lot of attention, but it'll happen one day. Space elevators. How many of you have heard about space elevators? Yeah, really neat idea, very romantic. From my perspective, totally impractical. Okay, the concept was invented in the 1880s by Konstantin Tsiolkovsky. It got a lot of popularity from Arthur C. Clarke's Fountains of Paradise in 1979. And the idea is that you hang a carbon fiber tether from geostationary orbit, where it takes 24 hours to orbit Earth, so in effect, you have the spacecraft hovering over one point on the equator, hang the tether all the way down to a ground station, and then an elevator just cranks you up and down. Makes it a lot easier. You just crawl your way up and back down. Again, this is still Newtonian mechanics. It's going to be action, reaction, of a different form, and electrical work. From my perspective, totally impractical, because the orbital debris, space debris issues, that tether gets, that elevator cable gets hit by something, you're going to have a very awkward day. Maglev, just have magnetic levitation, and use that as the first stage to get a rocket ship or an air-breathing vehicle, which is in the main illustration there, up to high speed at high altitude. So think of a ski jump working in reverse, going from Holloman up the side of the Sacramento Mountains, and you're on your way to space. Very real possibility for mining operations on the moon. So instead of using chemical rockets to launch materials back to Earth or into geostationary orbit to assemble structures. You would just put them on a maglev, which is basically an electric motor, but instead of in a circle, it's just one straight line, and fire it out. But again, it's action-reaction, and the fastest maglev in the world is out of Koloman. They set a world record about 2-3 years ago, 500 miles an hour. But maglev was not used to propel. It's the instead of having it ride on rails the way most of their rocket tests do, they levitate on the rails to help smooth out some of the vibrations and bumps that they would normally get. But it's the first step. Photon propulsion, another cure-all in science fiction, just use pure light. And the Project Starshot, which is developed a privately funded effort, Breakthrough Starshot, which is a privately funded effort to send a spacecraft to Alpha Centauri or some other nearby world, would have an array of multiple gigawatt laser systems beaming light onto a sail. Light has no mass, but it still provides a little bit of a recoil, a little bit of a kick when it reflects off of the surface. So if you're already in space, in the vacuum of space, weightless, enough light could indeed push you across the solar system. And we've already had some demonstration solar sails tested in Earth orbit, and we've used the technology with large flaps for some spacecraft in the inner solar system just to help trim the attitude to conserve station keeping fuel, or attitude control fuel. Okay, fantasy drives. Okay, for those of you who haven't seen it, don't get this reference, that is from Spaceballs. Okay, so you don't just go light speed, ridiculous and ludicrous. And of course, the special effects people have no idea what's going on, so you always go to plaid. They've got a great graphics computer, so wow, let's put some plaid up on the screen. The nation that controls magnetism controls the universe. How many of you remember the space coup with Dick Tracy? Not that many? Wow, yeah, it was... the whole space coup thing had to go away when we actually did put humans on the moon. Chester Gould had this notion that you could propel a spacecraft just with electromagnets mounted on it to pull on or push or pull on Earth's magnetic field and move you around in the interplanetary magnetic field, move you around through the solar system. The problem is magnetic fields here just aren't that dense. To get any magnetic fields that dense, you probably have to be around a magnetar, which is a highly magnetized pulsar. You don't want to be there because of radiation issues. But it is somewhat practical. Hubble Space Telescope, another spacecraft, is something similar. Hubble's attitude is controlled by gyroscope, basically giant gyroscopes, reaction wheel assemblies. You rotate them in one direction, the spacecraft rotates in the other. So by rotating the wheels back and forth, you can point and then hold on target whatever star or galaxy you want to observe. The problem is, after a while, those wheels are spun up to their maximum. If you put the brakes on, they're going to make the entire spacecraft tumble out of control. So what they do is they put the brakes on very slowly and gently, and at the same time, they turn on these electromagnets, and they drag against Earth's magnetic field. So this becomes the brake, and so they can unload those reaction wheels very slowly and gently without putting Hubble out of control. So it's a little bit of magnetic propulsion going on there. The Dean drop. How many of you heard this one? Back in the 1960s, Norman Dean claimed that he had a reactionless drive. That would be the holy grail. It's like perpetual motion. That's how most scientists and engineers view these sort of claims. Perpetual motion machines are impossible because friction is always going to rob something out of the system. If you had a perfectly frictionless system, you can't really use it except maybe as a battery, because the moment you start draining energy from it, it's no longer perpetual motion. Okay, he had a rotating system that supposedly reduced the mass of his test apparatus from about 9 to 8.5 pounds. He claimed that this could be scaled up and used for rocket propulsion, which is what's being illustrated there on the cover of Astounding Science Fiction in 1960. And it took in a lot of people. A lot of folks believed him, including our former curator, Harry Stein. But the thing is, he never produced a really working demonstration. He never really demonstrated. He never let anybody peek under the hood without, one, big wad of cash, he wanted a lot of money, and two, guarantee that he would get the Nobel Prize in Physics. Not making this up, which is kind of silly because if you really had something, just get a patent on it and you'll get lots of cash from that. And if it really worked, you probably would get the Nobel Prize in Physics. So it's vaporware. Transporters. Okay, one of the favorite things that we did in Star Trek. Roddenberry was asked one time, and he didn't invent the concept, teleportation. You turn your body into energy, transmit it somewhere, and then reassemble it, and you save yourselves the bother of going down to TSA, getting a ticket, goes to TSA, get boarded, take your shoes off, etc. Bam, here to there. Real easy. So somebody asked Roddenberry, why are you doing that? He said, because I couldn't figure out how to land the Starship. So you just transport them. The problem is, and you'll hear this mentioned if you're watching enough episodes of Next Generation, is the Heisenberg uncertainty principle. So in the Next Generation, they incorporated, they make a reference every now and then to the Heisenberg compensator. Discovery of the structure of the atom, and what's really going on at the subatomic level. Heisenberg said that you cannot know both the location and the energy state of a particle. That they're so tiny that just the act of observing disturbs the conditions. So you know where it was, but just by having looked at it, you have to send a photon or something in there, hit it, and come back and tell you this is where it was. So you can know where it was, you know what its energy was, but you can't know both. You've got to detect both to take their trillions and trillions and trillions of atoms apart and put them back together at the other end. If you don't do it right, things just don't get put that back together right. But they order in some episodes they would refer to really, really fast ships that would give problems as having transport drive. Basically, transporter would disassemble the ship here, bam, reassemble it light years away instantly. Wormholes, another favorite in science fiction movies. In shows like Stargate and Babylon 5 and others, wormholes are more reliable, just as great as the DC Metro. From here to there, mathematically, physically, from a physics standpoint, it's theoretically possible. It's the equivalent of taking a sheet of paper and curving it and punching a hole from one side to the other. So now you get from point A to point B faster than having to travel all the way around the sheet of paper. So space is multidimensional. The idea is, okay, if we could punch a hole through fourth, fifth, whatever dimension space, we could go from here to some other distant location in space, seemingly faster than the speed of light. Not violating that speed limit, but getting there faster, simply because you're punching from one side of the sheet of paper to the other. It was used most recently in the movie Interstellar, where there's a lot of stuff that they didn't do because the executive producer was Kip Thorne, world-renowned Caltech physicist who's also an expert on black holes. He literally wrote a book more than once on black holes, and he said there's certain things we're not going to let you do. So that's why, on many levels, Interstellar is technically accurate. But it's just a theoretical construct, and right now, they think that if it could be done, it would be at a subatomic level, and even then, it might not allow the movement of matter from one side to the other. Tachyons. These are not tachyons, that's just blue light. Tachyons, hyperlight particles. Theoretically, you could have matter with an imaginary mass moving faster than the speed of light. And as it slows down, its mass would be, its energy would become greater. So it could go at extreme velocities, but it could not slow down to reach the speed of light. It would still have that barrier. So tachyons have been invoked in various ways in science fiction movies as a way of getting hyperlight transportation. Tachyons are just theoretic. There's no proof that they exist. And I'm using this because theoretically they would produce a lot of gravitational radiation as they slow down. What's happening here is there are electrons traveling faster than the speed of light. And when they encounter the water, they give up their energy as blue light. It's called Cherenkov radiation. Okay, now wait a minute. Earlier I said nothing would go faster than the speed of light. I just said electrons go faster than the speed of light. I just violated my own talk. Wrong. The speed of light in a vacuum is what we're talking about. It is possible for matter to travel faster than the speed of light in a medium. This happens all the time because light goes slower. So the speed of light going through glass or through water is about a quarter to a third slower than what it would be in a vacuum. But you can have particles, subatomic particles, moving faster than light. And they give up that energy as radiation like this. So if you look at a picture of a nuclear reactor and there's this ghostly blue glow, that's what's happening. It's called Cherenkov radiation. The Russian physicist defined what was going on. So because tachyons don't exist, that's the picture that works for it. 0-point energy. How many of you heard chatter about that? 0-point energy. The idea is literally something from nothing. That at the quantum physics subatomic level, energy is constantly fluctuating back and forth. It will appear out of the quantum froth and then disappear. Energy and matter must be conserved. So on average, nothing is there. But you can have things arising. There are all sorts of fantastic claims about how you can power virtually anything for nothing using 0-point energy, but nobody's really demonstrated how it could work. So these things usually get lumped in with snake oil salesmen. Okay, NASA's warp drive. How many of you heard stories? So now we're getting closer. How many of you heard chatter about this in various news stories over the last 2-3 years? Yeah, supposedly NASA has a warp drive, and almost immediately pictures like this started popping up. It's entirely CG. It's based on an older concept called the M drive or the Kinney drive, which basically has electromagnetic radiation resonating in the chamber and supposedly net to thrust in one direction. There have been a lot of claims, counterclaims, and generally so far, everything that's come out of it is that if there's any thrust at all being produced, it's down in the noise level of the instrument, so we can't really measure anything yet. So again, perhaps a little bit more snake oil, but we've got some neat concept cars out of it. Okay, so the real deal, it's going to be done. Okay, Einstein said matter cannot travel faster than the speed of light. However, the fabric of space can travel faster than the speed of light. It's already done it once. The Big Bang, from about 10 to, let me get these numbers right, from about 10 to the minus 36 second to 10 to the minus 32 second, the universe increased in volume by a factor of 10 to the 78. That's 1 followed by 78 zeros. That's a few quintillion, quintillion, quintillion there. So the universe expanded. This is why the universe looks so big, and there's so much empty space between everything. The fabric of space simply expanded. If Mother Nature can do that, why can't we? Which is exactly what Miguel Alcubierre of Mexico City, get this title correctly, the name correct, the National Autonomous University of Mexico, in 1994, wrote a paper, Warp Drive, Hyperfast Travel Within General Relativity. And this is a result of Star Trek. As a kid, he was a Star Trek fan, and he started this as a thought experiment because he'd say, warp drive, okay, that kind of implies that you're bending space. Implies that you're bending space. Can't be space to be bent. He started this really as a lark, and as it started scratching out the math, he realized it could be real. It might work. So the idea is that you contract space in front of your vehicle and expand it in back. spaceship is riding in a little warp bubble in the middle. And it's moving at several times the speed of light from here to there. The crew is not experiencing any changes. Their mass does not increase. They do not undergo time dilation. Remember the paradox of the twins. If I send my brother out, my twin brother, if I had one, out to some distant star at the speed of light, and he comes back 10 years later, he's only 1 day older. I'm 10 years older. Because time dilates as you approach the speed of light. Actually, anytime you're moving, time dilates, but it doesn't really become appreciable until you're going really, really fast, getting really close to the speed of light. They would not experience that. So they could travel to another star system in a few weeks or months and age normally as if they had stayed home on Earth. So in that respect, it's a little bit more like Dooling, where the navigators who've been mutated by spice from planet dinner from Arrakis would fold space, so they traveled without moving. So conceptually it's a bit more like that. We don't have any spice available, so how are we going to do it? And that's the fly in the ointment. It would take manipulating lots of energy. It would take producing negative energy, perhaps even exotic particles in negative mass. There's some very, very unusual physics at work here that I don't understand, so I'm not going to try to explain it. And you would have to have the starship inside some sort of warp bubble structure protecting it. It would almost be infinitely thin, actually getting down to what is known as the Planck length, which is the theoretical smallest dimension that you can have in the universe. We don't even know if that's real. It's a neat little theoretical idea. So the shell protecting the spacecraft would have to be incredibly thin. Engineering problems, that's c squared, the middle should not be there. E equals mc squared. To propel even a small starship, the initial calculation is to propel even a small starship to 10 times the speed of light would require converting the mass of Jupiter into energy. We don't know how to begin to handle energy levels like that. And we don't even know how to channel that energy so that you would change space. You would create the warp field that would shrink space in front of you and expand it and back. Another problem? The shock wave. So the equivalent, the comparison that we're familiar with here, supersonic booms, you have basically the same thing, sort of an energy boom. All the particles in the front end of that warp bubble would be highly energized, and that energy would have to be dissipated when you arrived. So it would be kind of like the train pulling into the station. It's just as you get to the get into town, you set off a massive H-bomb. So pulling into the star system you're going to explore, and then setting off the equivalent of a gamma ray burst, not a good idea. But it's early days yet, very early days. Remember, it was 43 years from Gagarin's rocket to landing on the moon. If you want to be a little more patient, 700 years from Chinese fire rockets to land on the moon. So we're just starting the exploration. Perhaps we've already had the Chicago pile moment. Engineers at the Eagle Works Advanced Propulsion Laboratory at Johnson Space Center are experimenting with Alcubierre's oh, no, I don't want to update it. Jeez. Yeah, that's the problem with Microsoft. Oh. No, go away from Rocket. Talk about alien invasions, that's it right there. Eagle Works Lab at Johnson Space Center is experimenting with it. And oddly, what they're using is a variation on the same apparatus that Michelson and Morley used to measure the speed of light in the 1880s. very fundamental, very powerful device, much more than the interferometer. And what they're doing is they're trying to measure established conditions that at a microscopic scale might cause a little bit of that warp field bubble, and then measure if the instruments have been displaced just by a fraction of the wavelength of light, just using a conventional helium neon laser, deep red color. They're experimenting with it so far. The results are ambiguous. The answer is not yes. The answer is not no. And as I said, early days, we're still investigating it. Perhaps this is our Chicago Pile 2.0 moment. And all we need is a good supply of that lithium, and the universe is ours. Any questions? Yes?
One of the technologies we showed going to Mars in 6 weeks.
Yes, sir.
One of the G-forces, you tremendous, because you have to decelerate on the other end.
No, sir, you would not. In fact, in one article I was reading all the way back in the 1970s, this was a laser fusion propulsion system that I forget who it was. I think it was another Professor Rensselaer was working on. Proposed that you accelerate out at 1G, but then yes, as you said, you've got to put the brakes on. You can't just go to ludicrous speed and then stop like that. You have to stop about halfway around. You have to flip the spacecraft around and start decelerating as you just overshoot the mark in the solar system, which means it has to be extremely reliable, because you don't want to spend 6 months getting the darn thing fixed, and by now you're out past Pluto. But what they were suggesting was if you had a system where you could provide 1G acceleration constantly, so it's 1G, get the halfway point, flip it around, you're decelerating at 1G, that solves the problem of the really weird things that weightlessness does to the human body. So that would be very good for crew health. But so you're thinking in terms of like launch from Kennedy Space Center, where you're looking at 3 to 5 Gs. Of that for extended periods of time. No, that would not be good for crew health. But half G acceleration all the way out and all the way back would actually be beneficial. Anybody else? Either answered all the questions or everybody totally baffled? Yes?
How does the loose Higgs particle fit into any list, if any, at all?
Okay, the Higgs boson particle, the so-called God particle, which is the Large Hadron Collider up in the Alps, that we're working on, is what gives matter mass, as we understand it. I don't know. Again, as I said, for the Alcubierre concept, there is a lot of fundamental, very esoteric physics going on. And Mr. Scott is not going to be a steampunk engineer the way he was in the original TV series. He's going to be someone, there's going to have to be probably multiple Mr. Scotts, multiple different degrees, specialties in quantum mechanics, cryogenics, and all sorts of stuff to make this work. So the Higgs boson may figure into it, but again, it's an esoteric part of physics. My brother, he has this degree in particle physics. Yes?
Dave, if I may, I just want to tell everyone, I'm Sue Taylor, I'm the curator here at Space History. Next Sunday, November 13th, our Star Trek exhibit will be open to the public at that time, and there will be, within the exhibit, a 9.5-minute film entitled NASA Honors Star Trek. And I suggest very strongly, if you wish to watch, because many of the concepts that Dave was talking about today are contained in that film. So, thank you.
And we also have a transporter replica, so if you have difficult kids or grandkids, and stick them in there for a few bucks, we'll make them go somewhere else.
But the museum is not responsible for transporter malfunctions.
Yes.
I remember there was a movie back in around 1950 that I saw where they had, you were talking about the ramp, you know, for
Yes.
launching a rocket.
Okay, you're thinking of When Worlds Collide?
That might have
George
been,
Pal?
yeah, it was,
Yes.
yeah, it was right up a ramp and up.
Yeah, Tsiolkovsky and Goddard both, but this was theoretical calculations on that concept. And it still has its attractions. You have to find the right real estate, location, to do it. You want to have eastward facing, high altitude, like here, first mile of street, as they like to say in spaceport. And the concept that showed you, the vehicle was coming out of a tunnel.
Right.
So to get around the problems of atmospheric drag, you would be in a vacuum tunnel until the very last moment, and some massive gate would pop open, and bam, you're slammed into the atmosphere, and away you go.
And a number of years ago, at the air show that was over in Cruces, they had the competition with the what do you call it, the skyline or whatever it was, between various universities and so on, to see who would get up to the top of that thing, just to see if it was a possibility. They were doing it with solar panels.
Right.
Yeah.
You know, everything we're doing now
Yeah.
is still Newtonian mechanics for the most part, or basic electrical engineering. The Einsteinian Alcubierre fundamental quantum physics stuff. Maybe we can make it work, maybe we can't. Maybe the gamma ray bursts that we see with satellites are civilizations that have tinkered with it, and it didn't quite work out the way they wanted to. There's another movie for you. In fact, someone said there was a guy who was suing, a guy in white who was suing, went to federal court and demanded that the Large Hadron Collider be shut down because it was going to create a black hole, essentially go directly to the center of Earth and just suck everything in. And it got thrown at. The scientists all said, no, that's baloney. Because, you know, even as powerful as that thing is, the energies it produces are minuscule compared to what still happens routinely with cosmic rays hitting the upper atmosphere of Earth. It's just never there with instrumentation because they don't know when it's going to happen. And the federal court said, we have no legal standing. It's European, it's in the Alps, it's the U.S. court, go away. Okay, thank you for coming. Oh, yes.
Well, what about spacecraft design? Does that change with each stride, or
I'm sorry, what about now?
the spacecraft design designed a certain way?
That's a good question. Yeah, okay, my favorite all-purpose short answer, which my grandkids are tired of hearing, it depends. It's going to depend on what the drive system is doing. Aircraft today, the Boeing 777 looks pretty much like the Boeing 707 because you're still shoving a cigar tube full of people through the atmosphere, and the designs got tweaked, etc. But they still look basically the same because it's a tube going through the air. Spacecraft in the vacuum of space can be designed any way that you want because you don't have to worry about atmospheric drag. But still, basically, it's going to be the payload, the cabin, whatever. Up here, rocket down, you're pushing it, or slowing you down as you come down. With warp drive, no idea what it might wind up looking like because we don't know what kind of demands warp drive would make. The design that Roddenberry came up with, or that his production people came up with, was somewhat fanciful. They wanted things a little different. They incorporated a little bit of flying saucer, but not just directly flying saucer. A lot of the interior stuff wound up the way it was because the production designer had, I believe, had been in the Army Air Corps, and his father had been an oil field production engineer. So the guy knew how a lot of plumbing worked. But you know, that's just Hollywood props meeting our expectations. What the real thing might wind up looking like? Good question. Just about anything we do right now would be as smart as anything else. Yes?
On the boring aircraft, well, the seats got smaller. That's
Yeah. In fact, there was an ad in Aviation Week, in 1986 or 87 for an outfit that provided seating and everything for airliners. And it was a picture, it was an artist concept of sardine can being with a bunch of people slammed in side by side. It says, your aircraft look like this? Oh, wow, how did they come up with the design for our space camp dormitory? That's what we're doing with the kids. way, that does connect with his question. You might wind up with a really, really weird spacecraft design, but ultimately, if you have people on board, you got to worry about human butt width, height, etc. when you're designing it to keep the crew comfortable and to build it up from there. Any other questions? Okay, we got donuts left. Take them home so we don't have to eat them.
There's a donut or two, but before you go, let me just go ahead and applaud Dave. Let me tell you about a couple of upcoming activities that you may not want to miss. If you know anyone who is a teacher, please let them know that tomorrow is our teacher open house, and the majority of the activities, including registration for the open house, will be held in our theater building, beginning at 10 o'clock. So if you know a teacher, please encourage them to come. We're going to show them all of the really cool things that we can do to help them in their classrooms and help encourage students to go towards STEM education careers. The following week, on Saturday, November 12th, we will be holding our 40th anniversary celebration and the induction of Gene Roddenberry into the International Space Hall of Fame. There are a couple of things going on that day. First, in the afternoon at 1 o'clock and again at 3 o'clock in our theater, we will be holding the Trek Connection speaker panel, how Gene Roddenberry changed the world. And our guest speakers will be Bill Kraft, who spent over a decade of his life working towards having Star Trek commemorated on a U.S. Postal Service stamp, which was finally done in 1999. He'll be here to talk about that. And also, we have David Stipes, who's Emmy Award-winning special effects expert, worked on Star Trek The Next Generation and several other iterations of Star Trek, along with numerous other films and television programs that you'll find of interest. They will be talking about how Gene Roddenberry changed the world. Tickets for that are $10 in advance, and you can sign up for those on our website. That evening, beginning at 6 o'clock, we'll have a pre-reception on our second floor, and you'll be able to see the exhibit that our curator Sue and her team have been working so hard on. And then we'll come down here and we'll have dinner and celebrate our 40th anniversary with our keynote speaker, astronaut, and Senator Harrison Schmitt. He's a fascinating man and a very nice man. Following his talk, we'll hold the induction ceremony for Mr. Roddenberry. And following that, we'll go back up to floor 2B, where we will cut the ribbon for the new Roddenberry induction exhibit and Star Trek exhibit. So we invite you to also register for that. If you've not done so, we have very few tickets left. I will warn you. So if you want to attend that, please get your tickets as soon as possible. You can do that online, or you can go down to the education offices in the theater building and we can sign you up there. Next month's Launchpad lecture, I believe Sue is giving. Gemini, Mercury and Apollo, or some iteration
The wives
of
of the astronauts.
The wives of the astronauts, that was much.
Everybody knows about the men, but who knows about the women behind the men who, while they're flying around up in space, it's their wives down below that are having to put up with the press hounds, the publicity, having to get their kids to school. What are their kids going through? And, their husbands, they're just floating around.
So, Sue's lecture will be on the first Friday of December. We invite you to come back for that. Of course, that is free, and bring your friends. We'll have coffee and donuts one more time. Thank you very much for attending today.
Only one more time?